Hello, this is Littleton. I'm going to work a inverse Laplace transform problem here. We want to compute the inverse Laplace of 20 over s cubed plus 10s squared plus 16s. So let's start, just for convenience, we'll let x of s equal our polynomial 20 over s cubed plus 10s squared plus 16s. So what we want to do is we want to first break up this polynomial into smaller pieces that will be easier to compute the Laplace transform of. And so what we're going to do is we're going to use a method called partial fraction decomposition. And so the first step is to factor the denominator of our rational polynomial. So here we're going to factor out an s. We're going to get 20 over s times s squared plus 10s plus 16. Okay, and then now we factor this part into its linear factors. So our x of s is going to become 20 over s times s plus 8 times s plus 2. Or 2 and 8 are just the factors of this quadratic equation here. So now we're going to set up some coefficients, and we're going to say that this big thing is equal to a over some factor plus b over some factor plus c over some factor. And a, b, and c are completely arbitrary. You can use whatever you want. And for convenience, I'm going to just go from left to right. So the first factor, a, or is going to go under a, is s. Well, not like that. It's going to go under s, and then s plus 8 is going to go under b, and s plus 2 will go under c. And so now what we have to do is, of course, solve for a, b, and c. And you can do that in two ways. There's the one way you could cross multiply this times this and this times this, and then you can equate the s squared terms and the s terms and the constant terms and have a system of equations. But I'm going to do it a little bit easier way, and that is the following. So let's start with a. We can say that a is equal to s times our rational polynomial, 20 over s times s plus 8 times s plus 2. And we're going to evaluate this where whatever makes that particular factor 0. In this case, 0. So we're going to evaluate this at s equals 0. So we'll have 20 over s plus 8 times s plus 2, evaluate when s equals 0. And so you should get a is equal to 5 over 4. I'll write that a little better. 5 over 4. Alright, so we can do a similar thing with b. So, if we want to compute b and c, we can do the following. We say b is equal to its factor, s plus 8. Make sure you keep your parentheses. It completely changes the way you evaluate the thing. S plus 8 times 20 over s times s plus 8 times, well, that should be an 8. S plus 8 times s plus 2. Evaluate this where that makes s plus 8 0. So s is equal to minus 8. And if you evaluate that, you should get b is equal to 5 over 12. And for c, we have c is equal to its factor, s plus 2, times 20 over s times s plus 8 times s plus 2. Evaluate where s plus 2 is 0, so s equals minus 2. And you should get c is equal to minus 5/3. So this gives us a, b, and c, and an expression for x of s that we can easily compute the inverse Laplace transform of. That's going to be x of s is equal to the coefficient a, which was 5/4, times 1 over s, times 1 over s, plus b's coefficient, 5/12, times 1 over s plus 8, plus, actually minus 5/3 times 1 over s plus 2, plus, that's a plus 2. So now what we've created is an equivalent expression for x of s that is much easier to take the inverse Laplace transform of. So we'll do that by taking advantage of the linearity property of the Laplace transform, which says that if you have some constant a1 times a function x1 of t plus another constant times a function x2 of t, and you take its Laplace transform, then you'll get that constant times the Laplace of your first x of t, which we'll call x of s, plus your second constant times the Laplace transform of your second x of t, which is x2 of s. So here, and this is good for any number of terms, which here we have 3. So we'll start with the first one. We can take the Laplace of this term. I'll go ahead and pull out the 5/4. We'll have 5/4 times the inverse Laplace of 1 over s. If you look up in the Laplace table, you'll see that the inverse Laplace of 1 over s is just 1. So 5/4 times 1, which is 5/4. And for the second term, we will have 5 over 12 times the inverse Laplace transform of 1 over s plus 8. Again, from the Laplace table, 1 over s plus 8 is a form of 1 over s plus a, which the inverse Laplace of that is e to the minus at. So we'll have 5/12 times e to the minus 8t. And for the third term, we have minus 5/3. I'm going to do a different color here. Minus 5/3 times the inverse Laplace of 1 over s plus 2, which is similar to what we just did. So minus 5/3 e to the minus 3t, or excuse me, 2t. And that's your answer. So to express the answer, we will say x of t, which is what we originally wanted, is equal to the sum of each of these 3 terms. So x of t is 5/4 plus 5/12 e to the minus 8t minus 5/3 e to the minus 2t. And there's your answer.